like you to start by please finding the exact value of this integral. And yes, we actually can find this exactly. And so write it down and think through how could you actually find that exact value. All right, so looking at how we're approaching this problem, it's because of the type of equation it is that we can find the exact value. If I had given you actually the integral of something like x squared, or something along those lines, something that's more of a curve, we'd have a bit more trouble right now. We'd be having to use like a Riemann sum in order to estimate it. We wouldn't even be able to find the exact yet, although we will get there. But this one we can do, because think about what the graph of this would look like. If I graph 6 minus x, that means I start up at 6, and then I'm going down 1 over 1, a slope of -1. And we're specifically just looking at this section of the graph that's between 0 and 5. Remember what the integral means. The integral means specifically the area under the curve. Although we always say under the curve, it'd be more accurate to say the area between the graph and the x-axis, but everybody just always says area under the curve. That's what it really means. So what we're looking at then is finding what is this area. And because that is straight, we can do it. And as you go and find that exact value now, there are two different methods you could use. The most common method is break it up into two shapes along that line. The top one being a triangle. And so to find the area of that topmost triangle, I do 1/2 times the base, and it's 5 wide, so that's going to be 5, times the height. That triangle is 5 units tall. And so 1/2, 5 times 5 gives me 12.5. That's the area of that triangle. And then I could add to it the area of the rectangle that it's sitting on, which is 1 unit tall by 5 units wide, and so that has an area of 5. And so then to find the total area, I do 12.5 plus 5, and so we can find that the integral equals 17.5. Again, that's the area under the curve. Now I said that was just one of the ways you could do it. The other way, not that necessarily you needed to do it this way, but because I want you to see that you could, is you could have actually seen that what you're really working with here is a trapezoid. And so I could have just gone, let's trace it out in blue. Could have gone like that. If we had found the area of that trapezoid, area of a trapezoid is the average of the bases. So the leftmost base, the bases remember are always the parallel ones, so the leftmost one is 6, plus the rightmost one is 1. So I do 6 plus 1 over 2. That gives me the average of the bases, and I multiply by the height. The height is the distance between the bases, and so I'd multiply that by 5. And what do you suppose we get? Same thing, right? 17.5. Whichever way you chose to do it is fine, but I want you to remember that, yeah, we could go ahead and just do it as a trapezoid straight up. All right, now having done that one, hopefully then you'll be able to see how to go and do these 3 problems. 3 different parts here, A, B, and C. You have the graph shown. Please find each of those 3 integrals. So let's go ahead and do part A then. So part A, we're finding the integral from 0 to 2 of our function. Now, so that means from 0 to 2 like that. So we're just finding the area between those. In this case, then that means the area of this triangle. And so if I want the area of the triangle, of course, our formula is 1/2 base times height. So it's going to be 1/2. This triangle is 2 units wide, and it is 4 units tall. And so we end up finding that that total area then is 4. And so that is our integral. The integral then equals 4. All right, so then we go on to part B, where we're finding the integral from 2 to 6. So that means I'm starting here at 2, I'm going up to 6. So notice this includes our semicircle, and just a semicircle. So that means I need to now find what is this whole area down here. Well, it's a semicircle. So I start by finding just the area of a whole circle with the same radius. Notice our radius here. For instance, I go from 4 out to 6 or 4 down to 2. The radius there is 2. The area of a circle is pi r squared, so I do pi times 2 squared. And then for it to be a semicircle, I just cut that in half, so I do 1/2 times that. And so that gives us an answer of 2 pi, or about 6.28 if we go into decimals. Although there is a little bit of a problem with the answer we just found. It's wrong. Why? Why is 2 pi, or about 6.28, not exactly correct here? Yes, it is negative because it's going down below the x-axis. And remember, if it's ever down below, that means it is a negative area. And so, yes, I treat that as a negative. All right, and then finally, we go on to part C. And in part C, we're doing the integral from 0 to 7. So you notice that's the whole graph that we have from 0 up to 7. Well, we already have 2 of those areas, so we only need 1 more. We now need to find this area here. So it's a 1 by 1 right triangle. And so we have an area there of 1/2 or 0.5. If I then want to know this total area in part C, I'm going to take each of those areas, so 4 plus my negative 6.28, or the 2 pi if you prefer to leave it that way, plus the 1/2, or the 0.5. And we can go ahead and add all of those up together. When you do so, you should be getting an answer here of a negative 1.78. So then that's the total area under the curve between 0 and 7, and therefore that means it is the integral from 0 to 7 of our function. Now, something I want you to notice here. Doesn't seem like a really big deal, but it's going to end up being a big deal and part of what we're doing today and where we're heading with this. Because in order to do this, in order to find the total area between 0 and 7, really what we did is we found each of the individual areas, or in other words, each of the individual integrals, and then we added them up together. So we found that if I find individual integrals and add them, it gives me the same thing as taking the integral of the whole. It's little details like that about the integral that we're getting into today. We're looking at properties of integrals. And so we're going to be looking at actually 7 properties of integrals. This is the first 4. Go ahead and add these into your notes, and then we'll practice them, and then we'll take a look at the other 3. All right, and hopefully you got these into your notes now. Let's take a look and make sure we understand what each one of these is saying, why it is what it is. Our first one here. Notice in this case it's the integral from a to a. We're starting and ending at the same place. Think like when we were drawing rectangles to find the area. How wide is this rectangle? 0. And so its area then obviously would have to be 0, because regardless of how high up we're going, if it's 0 wide, the area is 0. This second one is one that actually is probably one of the most important to see, because it's the one that we can start saying, wait, you can do that? Because we introduced the integral notation in our last lesson, but we talked in terms of going from smallest to biggest. Well, notice here there actually is a rule that lets us flip that order. You can go biggest to smallest or smallest to biggest. The order actually can go either way. The thing, though, is that if you switch the order, then you also switch the sign of your integral. So, for instance, if you're going left to right and you get a positive integral, when you go right to left, you get a negative integral, or vice versa. All right, this one. Notice this is finding the integral of a constant. So, like, let's say you're finding the integral of 5, or something like that. Notice how we find that integral. Now, if we kind of think through this, this can make sense, but we really do need to think through it, because otherwise it's kind of an odd-looking little thing. Because if you graph a function like y equals a constant, so let's say we're using y equals 5. If you graph y equals 5, it's just a horizontal line. And if I want the area under the curve, it of course forms a rectangle. And if I want to find the area of that rectangle, it's the height, which is c, times the width, which I find by doing my starting point minus my ending point. And so really what this is just saying that, hey, if it gives us a horizontal line, then we get a rectangle, and so we do height times the width. All right, and the last one is actually the one that we've already used today. We just didn't know we were using it. Where if I want to find the integral between any 2 points, if I have two functions that are being added together, I can actually just take the integrals of each of those individual functions and add those integrals of the individuals together to get the integral of the whole. Now, I do want to practice that idea. And so here's 3 different problems that I'm going to have you try on your own first, and then we'll talk through together. All this information up here is what you'll use to answer it. We'll also use that same information across the top for our other set of practice problems. So you only need to write it down the once for the work that we'll be doing now and later. But once you have that written down, then do those 3 problems, please. All right, so let's take a look at these. For the first one, we are looking for the integral from 3 to 3 of, actually it doesn't actually matter of what. Because if we're taking the integral from 3 to 3, what's it going to equal? 0. Because if these 2 numbers, our starting and ending points, are the same, it's always going to give us 0. All right, next one. We're looking for the integral from 0 to 3 of f of x plus g of x. That means I'm going to take the integral from 0 to 3 of f of x. I'm going to take that value, and I'm going to just add it to the same integral value of g of x. So the integral from 0 to 3 of g of x. I can take each of those individual pieces and just add them to get the total. And so I'm going to end up doing 4 plus the negative 3. And so we should end up getting an answer of 1 here. All right, and then for this last one, it's talking about the integral from 3 to 0 of f of x. And you'll notice up above we have the integral from 0 to 3 of f of x. So certainly it would suggest that we're going to need to use that particular value. Remember, our rule is that if I switch my starting and ending values, it switches the sign of my integral. And so it's actually going to be a negative 4. Because I take whatever this value is up here, and I just switch the sign of it. If it had been a negative number, I would have made it positive. All right, and then these are the other 3 rules, or other 3 properties of the integral that we're taking a look at today. Add these also into your notes. All right, so then already in your notes, we got these. Let's double check and just make sure we get what each one's talking about here. So you notice that if we know that our function is being multiplied by a constant, and I'm trying to find that integral, I could just do the integral of the function and then multiply by that constant. Works the same way. The next one here, it seems like this would follow very naturally from addition, and it does in terms of how it makes sense, but it can be a little bit harder to see the whys and hows when we actually get into proving it. And so I went ahead and just, listed out separately just so we can be sure that we see that, yes, it still works with subtraction as well. All right, and then the last one here, notice the details. Notice in this last one, it's the first integral is from a to c, and the second integral is from c to b. In other words, if both integrals are to the same value at one of their endpoints, we can go ahead and we combine those integrals and get one total integral for that section. I'd like to put those into practice now. Same starting information up top here, so all this stuff is the same. Please use that to find these 3 values. All right, so for the first one, we're looking for the integral from 0 to 10 here. But you'll notice up here I don't have any integrals given that involve both 0 and 10. But what I do have is an integral that goes from 0 to 3, and then another one that goes from 3 to 10. And so I can use that last rule where I can put those together to get the total integral. So I'm going to end up taking the integral from 0 to 3, which is 4, and I'm going to add the integral from 3 to 10 value, which is 7. And so this integral from 0 to 10 must equal 11. All right, next one. Notice it's a number times f of x. So if I know what the integral from 3 to 10 of f of x is, and I do, I can just multiply that by the 3. So I do 3 times 7, which gives me 21. And finally, we're doing the difference within the integration. Well, if I'm going to do the difference, that means I can do the differences of the two individual integrals. So the integral from 0 to 3 minus the integral from 0 to 3. And so that's going to be 4 minus a negative 3. So you get 7.